Hello and welcome to the webinar A Beginner's Guide to D&T. My name is Markus Möller. I'm Head of Training Concepts at the GOM headquarters in Braunschweig, Germany. This webinar will be recorded as usual, so you can watch it again or share it with your colleagues. If you have any questions, you can ask them in the Q&A section. Stefan Siebold from the Product Management Department will answer them. We will show you at the end of the webinar where you will find the recordings. So what is on the agenda today? Well, first I will give you a brief introduction into GD&T, like intentions and concepts. I will show you some annotations in the drawings and what they mean. I will explain what steps are needed to derive a result in GD&T. We will have a look at the fundamental concepts of GD&T regarding their mechanical intention and evaluation in the GOM software. And I will not only explain GD&T on primitives, but also on freeform surfaces. At the same time, I will explain how these checks are computed and which mathematics work in the background. I will also give you an introduction into different standards. And finally, I will show you what product manufacturing information is and how to use it in the software. So let's begin with some definitions about GD&T. Well, first of all, it's a language that describes a part based upon drawings unambiguously. It is a library of symbols, rules, definitions, conventions to describe a part regarding tolerances based on size, form, orientation, and location. And it describes the function of a part or assembly using tolerances. And it accompanies the entire process chain from design over manufacturing to metrology. So let's have a practical example on a part of an assembly. The whole point of GD&T is to focus on the function of the part. The part we will use in today's webinar is the gray block, which is part of this assembly. The gray block shall be inserted into the blue block seamlessly. There should be no gaps between the two blocks. There is also a bolt that shall be inserted and should fit into the bottom and top block. So this is the verbal description of the function of the part. However, I have described everything verbally to you. Let's use another language to describe this, GD&T. This drawing describes exactly what I've just told you previously, but just in the symbolic language. What is the goal for this? Well, the intention is to describe exactly how to manufacture and inspect the part without room for text descriptions, interpretations, or guesswork. So let me explain the symbols. Here we have some symbols for flatness, here and here and here. We have symbols that describe perpendicularity here and also position. And you have also a certain size defined on this drawing. So I'm going to explain what that actually means. We have made this drawing and also manufactured the part specifically for this webinar in order to tell you the story you have seen in the previous animation. So the general question is, what describes an element regarding its function? Well, first of all, it's the size. Then also the form of an element is important. Of course, the position of the element and also the orientation. These four fundamentals are essential to describe a part regarding its function. You find this structure also in the menu structure in the software. The order here is also size, form, orientation, and location. So how do we derive a GD&T results? What steps are necessary? Well, first of all, there need to be a nominal information available that describes the element. Then the element will be produced. After that, the element needs to be captured with a measurement device. Then the point cloud will be extracted, like in this example, the computation steps for straightness. And finally, the extracted information will be compared with the nominal information, and deviations are calculated and displayed. Let's have a closer look on the size of elements. Think about the function of the borehole on our part. The bolt should go through our borehole. So obviously it must have a certain size to ensure that the bolt fits through. Imagine you have an inner cylinder like described in the previous animation. The bolt must fit through the borehole at any point. If the borehole is simply too small, the bolt cannot fit through. So it is important in this case to determine the minimum diameter to find the smallest hole of the borehole. And in order to find the smallest diameter, it is therefore important to have data available for the entire cylinder barrel. This also means that the element needs to be captured entirely, regardless of your measuring system. So this is a specification of which I'm sure you've all seen many times before. However, what does that actually mean? Let me make this more plain with this example. Let's assume that the measured cylinder looks in a section view like this. It is possible to calculate the minimum and maximum size for this. This is called a 2-point size. You may also calculate the maximum inscribed cylinder, or a Gaussian best fit, or a minimum circumscribed cylinder, or the envelope requirement, which is the same. You can see that different modifiers lead to different results, and the modifier should be chosen according to their functional purpose. If there is no modifier on the drawing, the LP is supposed to be used as a default. If any other modifier is explicitly mentioned, then this modifier overrules the LP. The GOM software supplies with all the different size modifiers inside the linear size function. Let me just come back to the example I've previously shown. An unambiguous drawing specification would look like this. The added modifier symbol describes now the functional intention regarding the size. I will show you now some size checks inside the linear size dialog in the software. So here you see our block we have designed and manufactured, and now I'm going to inspect here this cylinder, and in order to inspect something you have to construct it first, and as we are talking about GD&T here, I'm going to use a fitting cylinder. I will select it with Control and the left mouse button. The entire cylinder barrel here will be selected. And you could already choose here the method of computation. However, whenever you use an element in GD&T, the software changes the computation method in the background anyway. So I will just create it here. And now I will use the iInspect button here. For those who don't know, iInspect is a pie menu that offers you now the appropriate checks. So I have here a pie menu for GD&T, and right at the top you see here I have dimensions available. The independency principle and the envelope principle are just there for your convenience, as they are so often used. However, you can accomplish everything also with the linear size dialog. So I'm going to use that. So the software function opens, and the first thing I have to do here is I have to enter the nominal value for this cylinder. This is then of course specified on the drawing, which you have just seen. I can also enter here the tolerance, which was 0.1 millimeter. And I can also choose here the computation method. You see 2-point size is default, but you could also use any other modifier. So like in this case, the envelope requirement. And you can see that the values are changing depending on the modifier. So I will go just back to the 2-point size. And if you would like to find out more about the software function, please have a look at the direct help. You can access it here over the question mark. And here you find much more elaborate information regarding computation methods and background information. So if I just create this element, it gives me now the maximum and minimum size of this cylinder here. And this is also then indicated with these 2 blue arrows. And in this case, my check has failed. So what does it tell me? Well, it tells me my bolt won't fit through. And so already a major requirement has failed. So this is just an explanation for size. Let's continue with the presentation. Now I'm going to talk about form and form tolerances. As mentioned before, also form checks are important to ensure the function of a part. The form checks are straightness, flatness, roundness, and cylindricity. And I'm going to use now the flatness check as an example for form checks just in general. A typical drawing annotation could look like this. The arrow is pointing here at the bottom plane of our block, and the flatness symbol is here, and also the given tolerance. So again, let's think about the function in this case. The top block is supposed to lie flat on the bottom block, so there's supposed to be no gap between the two planes. In order to explain, I will exaggerate the flatness a little bit. So the actual measured object would look more like this. Flatness now means that every measured point must be within these two planes. The distance between those planes is the given tolerance of 0.3 millimeters, and therefore is also called tolerance zone. So how is it actually calculated? Well, here you see the exaggerated form of the plane, represented by the captured and selected measuring points. Now the software then uses a Chebyshev best fit algorithm to compute the center of those points. The Chebyshev best fit computes the resulting fitting element in such a way that the maximum distance is the smallest. This algorithm gives the plane its dimension, orientation, and location, of course. And the fitting plane is now the center of the tolerance zone. So as a next step, the software creates two parallel planes and moves them in both directions with an equal distance. The resulting zone is called the tolerance zone. The width of the tolerance zone is the given tolerance. The result value of this check is then the highest value from the center plane. Very important here, all points must be within this tolerance zone. Again, the flatness of the entire plane ensures the function. If only one point sticks out of this zone, the tolerance check is failed. So what you see in your result is the worst case error regarding the form, and is therefore again important to measure the entire plane regardless of your measuring system. So I'm going to show you this now again in the software. So I will just make this exclusively visible. So the plane we are going to use now is this bottom plane here. And again, in order to inspect something, I have to construct it. And I will use here a fitting plane again. I'll make the selection. And as this plane here is quite heavily distorted, I'm just going to extend this selection. And also here. So now I have made my selection over the entire plane. And again, the method of computation doesn't really matter at this point, but I will also give it a name and I will call it A. So this is my base element for the inspection. I can go again to iInspect and choose now the flatness check. And if I call the flatness check, the mathematics in the background are now changed, as I have just explained. And what you see here is now the tolerance zone. Let me just increase this a little bit so you see this a little bit more clear. So here you see the tolerance zone, and then the actual data must be within this zone. But in this case, the tolerance was given with 0.3 millimeters, so I choose that. And I have now here my result in the label, and you can also see the plane here is quite heavily distorted, so we are out of tolerance. In order to understand this a little bit better, you can open the properties window here, and if you go to display, you can say show color deviation representation, and this gives you a better understanding of the form error itself, so showing you this deviation plot here. And what we could do once again is to find out where we have the maximum. So I will just show the maximum deviation here. If I click OK, it computes me the maximum deviation. And then I do see here now my result. And the maximum deviation here is twice as high as this one, as the error can occur in both directions. And this color representation is a quite nice way to understand errors in the part and also to initiate countermeasures. So obviously this plane isn't correct. So the next question is, what do I do about it? So let's go back to the presentation. Now I'm going to talk about the third fundamental concept of GD&T, the orientation. So orientation can mean, is an element parallel to another? Is an element perpendicular to another element? Or has it a certain angle towards another element? Think about the function of our borehole on our part. The bolt should go through our borehole. It makes therefore sense to check if the borehole is perpendicular. However, perpendicular to what? So again, this is the borehole we are going to check. Regarding the perpendicularity, the feature control frame looks like this. So at the beginning, you have the information about the tolerance type, in this case perpendicularity. You have the given tolerance value, and you have also an information about the reference. And a reference in GD&T is called a datum. A datum can consist of only one element or several elements together. And we can now check in our case whether the borehole is perpendicular towards the bottom plane. And the bottom plane will serve here as a datum, and we call it A. So yet again, I'm jumping into the software. Just before I'll show you this, just one remark. If an element serves as a datum element, it makes sense to check it regarding its form. So, and the reason is that you need to make sure that whatever result you deduce regarding the orientation is not coming from the form error. So in other words, if your reference has already an error, it can be difficult to understand the orientation results because you already gain deviations from the datum. So in the previous demo, I've shown you the flatness check on the datum. If this check is already out of tolerance, as you can see here, it is not reasonable to use it as a datum. So in our case, the flatness is far out, and so it does not make sense to use it. However, we built the errors on purpose to show you some more obvious errors. So in real life has already one major player for the function failed, so the function cannot be fulfilled at this point. However, just to see or just to explain what happens next, I will use it anyway. So what do we have to do? In order to use a datum system, you have to construct it. So I will go to Construct, Local Coordinate System, Create Datum System. And then I will just simply select the plane A, and then it will be used as a datum. And you can also see that you have here remaining degrees of freedom, which means that the datum system here is not fully constrained. And this is already also a difference towards a coordinate system. A coordinate system needs to be fully constrained. A datum system does not have to necessarily. Remember, we want to use it for perpendicularity, so all we need is a plane, so it does not need to be fully constrained. So once I have created this, I have my datum system, and I will just get my cylinder back here. Here we go. And now we can check it regarding the perpendicularity. What do I have to do? Well, I have to select my datum system. I have to select my tolerance type, in this case a circular tolerance zone. And of course I have to enter here my tolerance, which was on the drawing 0.2 millimeters. And if we zoom in, you see again here the tolerance zone displayed, the circular type, and this axis now must be within this zone. Otherwise the check is failed, which it already has. So again, in order to understand this a little bit better, we can just increase the vector scaling perhaps as well. And so you get a better understanding of what is going on and more importantly, what to change. So in this function, you also see here different standards. So I'm computing right now according to the ISO 1101. My result looks a little bit distorted here, quite inhomogeneous. If I go back to the ASME Y14.5, I get a different result and it looks more homogeneous and more straight. So what's the difference between these computation methods then? Well, I'm just going to explain this in the presentation. So The ISO 1101, also known as Geometric Product Specification or GPS, and the ASME Y14.5, also more known under the general term GD&T. Now, just in general, the intention of both standards is quite the same, so everything I have explained until now applies for both standards. The difference between the two is more on a detailed level, which means the computations can vary slightly. So whenever there is a difference in the computation method, you can choose which follow to standard, which is usually then also specified on the drawing. And I will give you now an example of a different computation method for this perpendicularity. So how is it calculated? Let's see according to the ISO standard. Again, we have here our borehole and a little bit distorted. The nominal cylinder has also a center axis and is perpendicular to A. Around the center axis is the tolerance zone. Now, the center axis of the measured data must lie within this tolerance zone. The software will then compute the deviation between nominal and actual cylinder. However, this axis is not exactly straight, but looks like that it follows the contour of the cylinder barrel. So this is the result according to ISO. And so the question is, how is it actually done? And what the software does is, first of all, it computes the true center axis of a cylinder. And therefore, the software computes a Gaussian best fit over the entire cylinder based on the selection and via Gauss best fit. And then the software creates a section perpendicular to the axis. And then in each section, the software fits a circle, and the center points of all circles are connected to an axis, as you can see here. And since the axis is derived from the form of the envelope, this axis is called the true center axis of the cylinder. And you can see this more obvious in this distorted cylinder here, that the axis represents also then the form. So let's see how the perpendicularity is computed to the ASME standard. Well, first of all, the software restores the selection of the fitting element and uses the selection for the computation. And then it computes the center axis of a cylinder for the computation of the perpendicularity. Therefore, the software computes a minimum circumscribed or maximum inscribed cylinder on the restored selection of the element. So whilst the ISO also takes the form of the element into account, the ASME computes on a straight axis. And this is just one difference in computation. And you can find out more about the computation in the of the standards in the direct help of the software. So that was just the explanation for computation, also the explanation for different results you can have in the software. And let's continue with our fourth concept, the location. So those are, of course, important to ensure that the element is in the correct position in respect to a defined datum system. And location checks are position, tab pattern, concentricity, and symmetry. I will talk about line and surface profile later on separately. So, if we want to make sure that the bolt fits through the borehole, it must be at the right place. And the check for this is position. Again, the question is position in respect to what? So, also here is a datum system needed. In this case, we use the datum system ABC. A is the primary datum, B is the secondary datum, and C is the tertiary datum. The order is important and cannot be changed. So ABC is not equal to CBA. The secondary datum here is perpendicular to the primary datum, and the tertiary datum is perpendicular to the primary and secondary datum. So what does that mean? Let's take the example where the datum C is supposed to be perpendicular to B. So the datum B plane is indicated in blue. Now the datum plane for C will be moved perpendicular to B until it touches from the outside. And so you see in this extreme example that the datum plane moves towards the real plane from the outside and stops at the corner. And this approach requires a different computation method. In this case, it's Chebyshev again. There are different computation methods for different types of datum elements, like planes or cylinders and so on. And when you create a datum system, the software switches automatically to the correct computation method. So let's see what happens if we switch the datum system definition from BC to CB. Now, C is the primary datum and B the secondary datum. So B is moving perpendicular to C until it hits the plane from the outside again. So you perhaps notice that this leads to an entirely different datum system definition, and this is also the explanation why the order of datum elements cannot be changed. So what we need to determine, need to determine the position of the cylinder is the nominal information of the position. That means we need the nominal distance from the cylinder towards the datum elements. So these distances are called theoretical exact dimensions or also true positions. And you can find this, of course, on the drawing. So let me jump back to the software. So all I need here is this. I already have created and checked plane A. So all I need is plane B and plane C. So I will create those. And again, I will use just a fitting plane here. And I will call it B. And also this one here. And I call it C. So, and yet again, I will have to construct my datum system first. So I will go to construct, local coordinate system, create datum system. I will here choose my datum elements, B and C. So here you see now it's fully constrained. So there are no remaining degrees of freedom, and the resulting datum system is now here displayed. And if I just zoom in a little bit, so like this, or perhaps like this. There you go. You can see what I have just explained in the PowerPoint. This is the datum plane B, and this is C. So C has moved perpendicular to B until it touched here from the outside. So you see this really here on the actual data, exactly as I have explained before. So once I have created my datum system, and also maybe I just rename it with F2, and I call it a BC. I can now use this datum system to check the cylinder regarding its position. So in this dialog now, I have to select my datum system, and I choose my tolerance type again. And now I have to enter here the true positions, which you can then find on the drawing. In this case, -75 and -40. And so this is the nominal position, and this is also immediately here displayed. And I, of course, need also my tolerance. So that was 0.5 millimeters. And now you see my tolerance zone. And again, the axis is not in that tolerance zone, but sticks out. Again, if you show the deviation representation, you get a better understanding of what's going on. And of course, here again, you have a variation in computation. So you can choose the standard, which is then specified on the drawing, of course. So I will just create this, and this is then, we have checked it regarding its position. So let's continue with the presentation. So these are the fundamental concepts of GD&T based upon primitives like planes, cylinders, and so on. However, you will encounter in modern product development also elements which serve a functional purpose, which are not primitives but freeform surfaces. So, and I will give you now some insights of GD&T on freeform surfaces using surface profile. So take the top surface of this M, for instance. Let's assume this surface serves a functional purpose. I've explained before which fundamental concepts are necessary to ensure the function of the element. So how can you check the form, the orientation, and the location? And the answer is line profile or surface profile. So in the software, you can find the function line profile and surface profile. In order to explain the concept, I will focus on the surface profile. We could encounter on drawings two types of annotations. This symbol means surface profile without a datum system, and this symbol means surface profile with a datum system. So what does that mean for our fundamental concepts of GD&T? Well, the first definition will only check the form of the surface. It is the equivalent to the flatness checks for planes you've seen before. The second definition basically means that you have to use a datum system and therefore you have a reference. And if you have a reference, you can check both orientation and location as well. So in a nutshell, these checks can combine almost all GD&T concepts you have seen, except size. So size is not possible to check with these checks. But as you see, it is an interesting option to have one check that covers almost everything, and we will see how this develops in the future. So like I said before, surface profile and line profile are supposed to be used on freeform surfaces. So the question is, where does the nominal information come from? To describe a nominal plane geometrically is relatively simple, but how is it done with freeform surfaces? And the answer is, the nominal information has to come from the CAD data. So based upon the nominal surface, the software creates an infinite number of virtual spheres with identical diameters. The center of these spheres lies on this ideal surface. The diameter of the spheres correspond to the width of the tolerance zone. The computed value is the minimum diameter of these spheres so that all measured points lie within these virtual spheres. So this is basically done how it's computed, and let's dive into the software again. Let me just close my project here, and I will open surface profile. So here we have a CAD file. You see this M, we have the CAD available, and we have also the measured mesh. And what do I need to do in order to gain the nominal information here? Well, I have to construct it. So I go to construct, surface, patch compound from CAD. I will select the CAD patch here with control on the left mouse button, and I can immediately create it. And of course, we also need the corresponding actual element, so the fitting element on the mesh. And therefore, we use something called measuring principle, is then obviously fitting element, and it does compute the actual element now on the measured data. So, and once again, I can use the pie menu here to select surface profile. And as I have described, you can now either use a datum system or you do not use a datum system. So in this case, I don't use a datum system, and that means my result here I see only tells me something about the form. So like the equivalent to the flatness check. So let's continue with the last topic for today. And this is called PMI. PMI stands for Product Manufacturing Information. What does that mean? Well, in modern product development, modern product development takes place mostly in 3D. So you have the design in 3D, you have the manufacturing in 3D, and you have the metrology in 3D. And the idea is to have also the drawing information in 3D. So rather than defining everything on a drawing, the inspection information is directly attached to the CAD data. So all the information like nominal elements, checks, tolerances can be imported with the CAD data. And PMI can include but not necessarily have to, can include geometric dimensions, tolerances, 3D annotations, surface finish, and material specifications. The supported formats we do are CATIA V5 and V6, NX, and Pro E. And we also have a knowledge base for more information and specification in our support area. So just go to support.com.com and then knowledge base, and there we'll find something for PMI. So I will just give you a very quick live demo to tell you, or to make you understand what that actually means. So here I have a CATIA CAD part, and that contains this PMI information. And if I just import this into the software, I see the normal CAD import dialog. And I also see, like here in the export parameters, sometimes you have to unfold this, check PMI data and load them. And if they're available, you can choose here, yes. And if I do this, it now imports not only the CAD data, but it imports also all nominal elements or inspection elements and also tolerances, basically everything you need for the inspection. So you see, this is already done. So I do not need to do the inspection of this. What I need to do now is, of course, I need some measured data, which I've just imported. I need an alignment, which I'm just doing right now. And what I have to do next is, of course, to tell the software what to do regarding the actual elements. So I will use iInspect again, and I will apply to all these elements the measuring principle fitting element. Again, computation method doesn't really matter, as it is changed automatically anyway. And then the software takes a little while to create all the actual elements and to perform the inspection based on this nominal information. But eventually, everything will be computed, and you see you get all your results here. So you basically skipped all this part, looking things up on the drawing, constructing them, and so on, and entering tolerances. You just have this information already in the CAD file included. So it's just an interesting concept. So after all these explanations and demos, I think we could summarize the topic in one sentence, and I think we could think of GD&T as it tries to simulate mathematically functional mechanical requirements. I think that captures more or less the essence of the whole concept. And everything you've seen today in the live demos can be done in the free GOM-Inspect software. Just go to gom-inspect.com to download it. And if you would like to try out GOM-Inspect yourself, you can use the video tutorials to become familiar with the software. We have created 6 video tutorials that explain all software concepts in just a few minutes, and you will find them on the GOM Metrology YouTube channel. And also, you will find there some What's New videos we've made about GD&T. We have created those for the software version V8 SR1 when we had a lot of new functions. So you find there more information such as projected tolerance zone or common datum systems and so forth. So as mentioned at the beginning, this webinar was recorded. You will find the video for download in the support area and also on the GOM Metrology YouTube channel. We will try to upload this recording sometime tomorrow, so should be ready for the weekend. And we also have a dedicated training course for GD&T, and we have developed this together with the company DIM. It is a 3-day training course, and it goes much deeper into theoretical background and practical exercises as I was able to do in just this short time. But there's, in essence, I think I've captured the essential things. But of course, here are much more details about material requirements and so forth. So if you're interested, have a look on our website and then you find more information about this training. So this was the webinar, A Beginner's Guide to GD&T. We will stay online for a while to answer further questions in the Q&A section. I see Stefan is busy typing. And thank you very much for your attention, and we hope you enjoyed it. And have a nice day, and auf Wiedersehen.